Hello dear friends, today's discussion is quantum mechanics. So friends, I am talking about quantum mechanics and illustrations of spin half system. Before illustrations of spin half systems, I want to discuss postulations. So quantum mechanics has four postulations. One is state gate. Corresponding to a physical system, there is a complex vector space. Every state of the system is represented by k vector in this vector space. Number two is operator. Every physical quantity is represented by Hermitian operator that acts on the vector space of the system. Number 3. Eigenvalues of the operator. The result of every individual measurement of a physical quantity on a state of the system is one of the eigenvalues of the operator corresponding to that physical quantity. After the measurement, the general state of system changes to the eigenstates corresponding to the eigenvalue. Number 4. Expectation value. When the initial normalized state of the system is bra vector alpha, then probability of getting, it is not bra, it is k vector alpha, then probability of getting the eigenvalue A, the result of the measuring physical quantity A, is inner product between A prime and alpha square of that. What is the probability of getting a particular eigenvalue? System undergoing quantum jump from a general state vector to an eigenstate of the operator. Average of a large number of measurement of A in the state is given by the expectation value. Expectation value A, the angular bracket is the notation for that, is bra vector alpha, operator ket alpha, bra vector alpha, operator ket vector alpha, operator ket alpha. And we explained this bra vector alpha and ket vector alpha in terms of the eigenheads of A. That is the term of k prime, or we express the operator A itself in terms of its eigen A. Note, operator. The need to introduce the mathematical notion of an operator into quantum mechanics can be motivated by the recognition of a fairly obvious characteristic of a physical system. It will evolve in time, that is, its state will be time dependent. But a change in state could also come about because some action is performed on the system, such as the system being displaced or rotated in space. The state of multi-particle system can change as the consequence of particles making up a system being created or destroyed. Changes in state can also be brought about process induces on every state of the system, that is a table of the possible before after states. A mathematical device is known as an operator. The operator representing the above physical process is mathematical object that acts on the state of a system and maps the state into some other state in accordance with exhaustive list proposed above. Linear and antilinear operator. There is essentially no limit to the way in which operators could be defined, but the particular importancy are operators that have the following property. If A is an operator such that for any arbitrary pair of states kth vector psi 1 and kth vector psi 2, and for complex number c1 and c2, that this is linear operator. See, the property is follows, linear operators property follows. This is the linear property. Okay, I hope I can clear this concept. In quantum mechanics, operators are, with one exception, linear. The exception is the time reversal operator, which has the property this. This is the time reversal operator. This is not really linear. This is antilinear. Bracket notation. Now we are discussing bracket notation. Write the inner product as u by v. Instead of uv, we call this is the kth, which is element of vector space of v, and this is bra, which is an element of dual vector space v star. And uv is equal to v by u star, and v equals to 0, v equals to 0, and this is the first, second and third, 4, 5 and 6. Eigenkets and eigenbras. The notation of eigenstates has been introduced above kth vectors, in which case the eigenstates could be referred to as eigenkets. The same idea, of course, can be applied to bra vectors. If for some operator a cap there exists a bra vector phi such that phi a cap is equal to a phi bra vector phi. Phi is said to be eigenbra of capital A, and a phi is the associated eigenvalues. Must remember, a phi is the associated eigenvalue. The eigenvalues in this case can have the same array of possible properties as listed above the eigenkets. Illustration of spin half system. Now friends, I am discussing illustrations of spin half system. So friends, you will see the diagram. This is, I have already drawn a diagram. So let's start to discuss. I have to find out Sx, Sy and Sz. The third part of the sequential measurement. This is my third part. I will discuss third part of the sequential measurement. So what you see, that the output, you will see output corresponding to S equal to plus corresponding to S equals to minus. This is my output. These two beams are of equal intensity. These two beams are equal intensity, means the probability of getting a particle in this beam, probability of finding a particle in this beam. What is the probability? The kth plus and kth minus are half. Two beams are equal intensity. We can conclude that these two beams are having equal probabilities to be in this state, that means half. So probability of find the state in the bra vector side initial state on the skate vector side and take the square of the inner product bra vector plus. So inner product final state on the bra vector side and initial state is skate vector side. So you will see which is final. This is the final state is bra vector side. Final space state is bra. This is not final. There is final state. This portion not. The final state is bra vector side vector and initial state on the kate vector side. Kate vector side. So this is the result and is equal to half. And this can be complex. This is complex. Similarly, we can get bra vector means minus into sx plus kate vector whole square equal to half. Two beams has equal intensity. Introduce phase factor here. So if it's a real number, then if you take the square, it is plus or minus. Plus or minus. So what we get? We get plus sx plus equal to e to the power I theta 1 half. There is no change in the observable result that the two beams are equal density. We can reduce the phase factor. Here, similarly for this, minus sx equals to e to the power I zeta 1 by root 2. This is also 1 by root 2. Sorry, it is not 1 by 2. Expansions function. So what we get? We can get sx plus equals to e to the power I theta 1 by root 2 plus this and e to the power I xi 1 by root 2 minus. And this portion I will take common I theta 1. So whatever I get 1 by root over 2 plus and e to the power I xi 1 minus theta 1 by root 2. This is the minus. So overall phase factor, this is the my theta 1 is overall phase factor, and this portion is my relative phase factor. The difference in phase factor between Kth minus and Kth plus between two base, the overall phase factor does not make any difference to the state Kth. Zeta 1 minus theta 1 equals to del 1. And Sx comma plus equals to, I can write 1 by root over 2 plus e to the power I del 1 by root 2 minus. We do this experiment, the input beam is this. If the input beam is this, then the output will be the same, half intensity or equal intensity. That means the probability is 50. We can repeat this argument a bit that then we will end up with the similar result here for Sx. Minus equals to 1 by root over 2 plus e to the power I eta 1 by root 2 minus. Orthogonally relationship between them. So orthogonal relationship between them, Sx bra vector, this is bra vector Sx minus and Sx Kth plus equals to 0. So what is the bra vector have to take adjoint of each term. Kth plus and Kth minus are mutually orthogonal, so that will be 0, and Kth plus and Kth plus are normalized. So friends, e to the power I del 1 e to the power eta 1 is equal to minus 1 after simplifications, and e to the power I eta 1 is equal to minus e to the power I del 1. This is constraint relationship. This relationship is constraint relationship, and Sx plus is equal to 1 by root 2 Kth plus e to the power I del 1 by root over 2 Kth minus Sx comma Kth minus equals to 1 by root 2 Kth plus e to the power minus I del 1 by root 2 Kth minus. Multiply the projection operator corresponding in terms of those eigen Kates. So Sx is equal to plus h bar by 2 Sx comma plus comma Sx comma plus minus h bar by 2 Sx comma minus and Sx comma minus. So in the form of projections, Kate is Kate minus normalized and Kate plus normalized. So what we get? We get h bar by 2. Our result is e to the power I del plus and minus plus e to the power I del 1 minus and plus this. This is the Kate plus, this is Kate plus, and this is bra minus, and this is my Kate minus, and this is bra plus. So Sx plus is equal to Sx. This is Hermitian operator. This operator is called, this operator is Hermitian. This operation Hermitian operator. We have done sequential Sternum experiment from the observation standard leg experiment, this time second stage. Now we are discussed second stage. Now we are discussing the second stage. A beam is moving in the z directions, and first we are measuring Sx. Okay, the particle are in Sx state and half in Sx 8. We take Sx state that measures by its being. We get two beam intensities. This is the, here is the 2000 particle. Here is 2000 particles. Is this beam? This beam is 1000. This beam is 500. So intensity is half. So let's start to solve this. So which is our, this is the bra form. This vector should be bra form. Similarly, you will see that this portion, this plus is also bra form. This is the bra form we will write, and this is Kate form. This is Kate form and this is bra form. So we are doing same way. In here it is bra form. We will write it as a bra form. So it is Sy plus, and this portion is also Kate form. So it is Sx comma plus, and this is whole square is equal to half. So again, this value I have found this is the value. This value I have already found in here. This is my values of Sx and Sx plus and Sx minus. Similarly, if we will work in here, so we will get 1 plus minus e to the power I del 1 minus del 2 whole square is equal to 2, and we can write this way: 1 plus minus e to the power minus I del 1 minus del 2 plus minus e to the power I del 1 plus del 2 plus 1 equals to 2. So cos del 1 minus del 2 is equal to 0. So del 1 minus del 2 equals to pi by. Now Sx, the summarizations. Now I will discuss summarizations of summarized. So L half system, S half system. So Sx comma plus minus kth vector is equal to 1 by root over 2 plus bra plus minus e to the power I del 1 divided by root over 2 minus kth minus, and Sx is equal to h bar divided by 2 into e to the power minus I del 1 plus bra plus and bra minus, and e to the power I del 2 kth minus and bra plus, this is bra and this is kth, and Sy similarly we can find out Sy is equal to h bar 2 e to the power minus I del 2 kth plus bra minus plus e to the power I del 2 kth minus bra plus. So del 1 minus del 2 equals to pi by 2. Put del 1 equals to 0, so it is plus minus I write. So del 2 is equal to plus minus pi by 2. So whatever we get Sx plus minus 1 by root 2 kth plus minus. So Sx is equal to h bar divided by 2 plus kth plus bra minus kth minus bra plus, and Sy plus minus equals to 1 by root 2 bra plus kth plus plus minus 1 by root 2 kth minus, and Sy is equal to h bar by divided by 2. It is also, it is I divided by root 2, and minus I kth plus kth minus plus I kth minus bra plus. So thanks for watching, friends. If you will I will create a lot of video based on quantum mechanics.